Yes.
Okay. First of all, very good afternoon to all of you. Myself Rajesh Purkait, the assistant professor of CSE in ITER. We are going to start our today webinar sessions on the topic of the art of cellular automata. Before going to start, I want to introduce to all of you with our today guest and my friend, Dr. Souvik Roy. I express my warm welcome to our today guest, Dr. Souvik Roy, for accepting my proposal. He is currently working postdoctoral research at C3I Hub in Indian Institute of Technology, Kanpur. He is also a researcher at Cellular Automata, India. He received his PhD degree from the Department of Information Technology, Indian Institute of Engineering Science and Technology in Shibpur. He was published his research work on cellular automata in different reputed journal, conference, and as a book chapter. His research interests are complex system, cellular automata, pattern formation, and chaos. So I would now requesting to my friend Dr. Souvik Roy to share his, I already he has shared her screen to start the webinar presentation.
Thank you very much, Rajesh, and thank you very much for the invitation from Shiksha Anushandan University, Bhubaneswar. So I'm just sharing my screen. So the screen is visible?
Yes. Your screen is visible. Yes.
Okay. The title of the talk is The Art of Cellular Automata, and another subtitle is, I have added another subtitle last night, How Does Robust Computation Exist? So let me start with a few initial motivations. So this is a screenshot of a news that it says that deactivation of a flash, for the deactivation of a flash, the Chinese railway system is down for 1-2 days. So the problem is that the new machines of these Chinese railway systems are with different configurations, and in the old machines there are some flash system, and the person installed this system already left the company, and in one machine there is a deactivation, and for this small fault the whole Chinese railroad system is collapsed. The point I'm trying to make it that in our life, in our each and everyday life, in societal systems, technological system, for a small fault, sometimes the whole system actually collapsed. This is the first initial word. Then I'm trying to put the second initial word, that then how do we explain the robustness of living organism? You can see the picture, there is a living organism there, and if you see the pattern in this living organism, you can obviously understand this is a pattern. And so from that pattern, there are some the triangles are not symmetrical. There are some noises in this pattern, and so therefore this noise or small fault is not only part of our technological things, also part of our evolution and all these things, real life are living organisms also. And so the question I will try to address is that what is a good model with this robustness for physics, biology, economy, and obviously the patterns coming from it. So there are two type of the talk are divided into two parts, and they are going on parallelly. One part is the patterns we are coming from uh, one mathematical model. The model is very easy enough, and also what is the effect of noise in this model. So, and finally we are trying to understand the question, how does the complexity of complexity combine it with this robustness. So here the complexity, I don't mean the traditional complexity theory, so something different from that. So obviously another initial word starting with Turing. So here I'm mentioning Turing not because of that Turing is the starting point of everything in computer science. Here I'm not mentioning about Turing machine, I'm mentioning about another paper of Turing, the chemical basis of morphogenesis. The paper published in 1952, and if you read the abstract of the paper, Turing trying to say what he trying to say is that so from one cell the other cells are grow. Suppose there is an egg, and from one cell the whole egg is grow, and from that egg suppose a bird is coming out, and so the structure of the cell, one cell is same. So from the other cells, from one cell the hand will coming up, one cell the leg will coming up. So how it is possible? And the answer here Turing coming up with that there are some noises, and from that noises from one cell the hand will come up, from one cell the leg will come up. So this is the also if we visit the morphogenesis, so just because of from one cell another cells are creating. So this is the effect of noise, that these cells are evolving differently. And so so this is the initial motivation. So we want to study first of all the noise, and uh, starting from Turing to technology, all these things are related with this noise. And now the, the point of study here is one mathematical model. So now I'm little bit talking about this mathematical model. So the point of this mathematical model is that when we see the birds in the sky, they're moving together, turning left and right, or if we see the ant in our house walking in a line, we often think that there is this leader which one is leading the flock of birds, and the rest of the birds are just following that leader bird. But in reality it is not right. In reality each and every bird interacting with their neighbors, they are decide collectively, and from this local interaction between these birds the global behavior is reflected. So that's the philosophical point behind this mathematical model. And the name of this model is my friend Cellular Automata. So I'm defining a very easy mathematical model, uh, and let's see what things are coming up with this simple mathematical model. So the model says that there is a one-dimensional array or lattice. So there is a one-dimensional array, and there are cells in this array, and each and every cell is associated with two states. So let's say 0 and 1. So here in this picture, white for 0, 1 for 1. Sorry, this color is for 1. And each and every cell will interact with their neighbors only. So their left neighbor, right neighbor, and self. So depending on depending on observing their left ribbon, right ribbon, and self, each and every cell will change their state. So there are 8 possibilities. So if we consider the self, left, and right, so self, left, and right, there are 8 possibilities: 0, 0, 0, 2, 1, 1, 1. So, and depending on these possibilities, they can change their state. So suppose if there is 0, 0, 0, it will become 0. If it is 0, 0, 1, it will become 1. The middle cell will become 1. So this is the rule. And we'll consider periodic boundary condition. That means this cell, this right side cell, is a neighbor of this left side cell, and vice versa. So this is the very basic mathematical model. One can easily program it by spending 10 to 15 minutes. And and each and every time step, the array will evolve. So the first time step, at the initial configuration, all the cells are in 0, the middle cell is in 1, and the rest, all the cells are in 0. In the second time step, this cell will be updated, this middle cell, all the cells will be updated, but the rest of the cells are following this rule, 0, 0, 0, 0. So therefore they will stay in 0. So in this cell, there is a change. This will become so this cell is 1, 0, 0. So it will become 1. So now for the left cell of this one cell, so 1, 0, 0. So according to the rule, 1, 0, 0 is 1. It will become 1. Then this one, 0, 0, 1. So according to the rule, 0, 0, 1, this is become 1. And if we apply for this cell and rest of the 1 cells, it will become 0, because 0, 0 is 0. So all the cells are updated following this simple rule. And how many possible rules are there? So if we follow this scenario, then it will become 0 or 1. So therefore 256 possible rules are there, and we'll evolve the system. That's all. That is the mathematical model, nothing else. So very simple model. You just update one array following a rule, and the rule is depending on left, right, and self state. So that's, if you evolve it, it will show that kind of behavior. Okay, so let me now say it seems that the model is very very simple, and what we can do with this kind of simple model, because this is a class first year programming language. Question may be asked by stating this model, that you will take an array, the array states will change at each and every time step following a rule. So this is the model, nothing else, no complex mathematics, nothing. So let me show. So this type of rule, 256 rules are possible. So we will name this rule following this fashion. So here are 5 examples of these rules. So if 0, 0, 0 is become 0 for the first rule, 0, 0, 1 become 1, 0, 1, 0 become 1. So following this fashion, and we'll take some decimal value of increasing order decimal value of these things. So if it is 1, we'll add 2, and we'll represent that rule in a decimal value. This whole rule will represent as a, for simplicity, nothing else, for calling this rule. Otherwise we have to call this rule by 0, 0, 0, 1, 1. So you just take the decimal value for representing these rules. And here there are, so what are the possibility? The first possibility is all 8 bit are 0, the rule 0, and the last is all 8 is 1. This is 255. So 0 to 255, there are 256 rules. And now I'll show the evolution of this rule starting from different initial configurations. And you can see that with this simple program, this is absolutely simple. One first year student can able to program it easily. I'll show that from this simple program how complex dynamics are emerging, and I'll also try to show that from that simple system Even we can do complex technological applications like pattern classification, like random number generation, like design of crypto system, all these things. So let me first show a few uh, evolution of few rules. So till now, is it clear? Everything clear? Is there any question? Okay, I'm assuming
So if
that.
the students will have questions, they'll also put in the chat box. So
Okay,
towards
If
the
anyone
end,
have
we
any
can
questions,
take it to.
okay, fine. So let me proceed. Now I'm showing the evolution of such a simple system. So let me run the program. Let me run the program. So I'm taking rule 30. That means 0 0 something. The decimal value will be 30, and it shows this kind of dynamics. If we run it again and again, each and every time step, the array will change their state, and I'm just plotting that state in some graphical representation, nothing else. So I'm starting with a random array, random initial configuration, and I'm evolving the system, and it shows this kind of dynamics. This is rule 30. And you can think that just recap that I have shown you one uh, living organism picture. Okay, so the pattern in that living organism is exactly similar as this pattern. Okay, so now let me stop this simulation. Let me simulate it again. Let me simulate it again with rule 30, but uh, the initial configuration is the middle cell is in 1, rest are in 0. So it shows this kind of dynamics. It evolving, middle cell is 1, rest are 0. I'm following this rule 30, and it shows this kind of dynamics. And now you can think that, oh, this is a very simple thing, very easy to program. So what is exciting about it? I've shown one exact example. Now let us talk about some real business. So this rule 30, there are prizes of $10,000. Sorry, $30,000. So there are three problems of this rule 30, and there is a $30,000 price, almost 1 crore 25 lakhs something. So if you solve this problem of this simple mathematical system, then you will get $30,000. So what are the problems? The problem is that, does the center column always remain non-periodic? That means this center column will always remain non-periodic. This is the first question. The second question is, does each color of cell occur in average equality of the center column? And the third column is that the third question is that, does computing the nth cell, okay, so for computing the, suppose this is the nth cell, is it possible to identify the state of the nth cell without computing the previous states? So you have to say what will be the nth cell in the middle column without computing the previous state by formulating some mathematical equation. So that is the power of this simple mathematical system. Even uh, this simple mathematical system, which can able to uh, write program easily within 10 minutes, we can't able to characterize the properties of the system. It is showing completely chaos, and from this chaos we can create random number. From this chaos, uh, cryptography will come. So that's the beauty. I'm stopping it. I'm showing. So this is the dynamics. If we plot the picture, this is the dynamics. Okay. So this is one rule. There are 256 rules. let me show few more rules for because there are different kind of rules. So if we run rule 1110, so this is the dynamics of rule. Let me stop this. Let me start with random initial configuration. So let me start with random initial configuration for rule 1110, and oh, I'm putting 100, not 1110. So rule 1110. So this is the dynamics of rule 1110, and one person from Switzerland, Cook, have proved that this dynamics of rule 1110 is equivalent to universal computation. That means whatever we can able to do with our Turing machine or mathematical model of Turing machine, so with this rule only, we can also able to do the same thing. The Cook has proved it. So this model is equivalent to universal computation. So this is another exciting point, that whatever we can able to do with Turing machine, the universal Turing machine, we can also able to do with this simple model. So this is kind of exciting mathematically, but we'll focus on more on technology rather than mathematics. So let me show few more rules. I'll show one rule that is 184. Let me show 184. So observe this rule. What the rule is doing, it just shifted the distance of two ones. And this rule is the traffic rules. This rule is used for modeling traffic. That means if there are several cars together, by following this rule, by putting some signals, we can create a distance between two cars. So this rule is used for modeling traffic. So there are few simple rules. These rules are simple, and there are few quite chaotic rules. Few rules which are chaotic. So with simple rules, we can implement simple kind of modeling, right? Modeling of traffic and all this. Of course, we have to put some more complicated things for modeling traffic with this rule, but this is the basic model. And with these chaotic rules, we cannot build straightforward technology, but we can use it for random number generation and all this. So this is a cellular automata. So today I'll talk about noise. I have mentioned already. So in this simple model, I'll put some noise, and I'll check that the effectiveness of this noise. So I'm planning to show two kind of noise, but let me check how much I can proceed. So the first noise is fully and alpha asynchronism. So this fully and alpha asynchronism is what? Previously, what happened is that previously all the cells are updated at each time step. Now I'm putting some noise, and the noise is that each cell will update it with some alpha probability. So now I'm saying that, okay, in the previous model, all cells are updated together at each time steps. Now in this noisy model, I'm saying that, okay, but reality is not synchronous. In reality, every persons of a same town will not eat at the same time, will not sleep at the same time. So therefore, the reality is asynchronous, and we will update each and every cell depending on some probability. So depending on this probability value, the cell may be updated, may not be updated. So that's the noise I'm adding in this model. Let me show how the behavior changes. So let me again run these programs. So let me again start with rule 30. So this is the synchronous version, or without noise version of rule 30. All the cells are updated together. Okay, so now let me put some noise. I'm saying that each and every cell will be updated with 90% probability. That means there is a 10% chance that a cell will not be updated. And let me check the difference in the pattern. Okay, so I'm putting 90% probability in the same rule, and this is the behavior. Okay, behavior seems somehow same, but some simplicity comes. Look, observe this pattern. Previously there are more chaos, now some simplicity come. Let me increase the rate of noise. Let me increase the rate of noise and observe. Let me increase the rate of noise. Let me put 0.7, and we can see that more simplicity will come. The behavior became more simple. That more simplicity. These are the patches of simple things. There are chaos, but there are local chaos. The simple things come between the chaos. Okay, so let me increase the value of noise more. Let me make it 0.5. So it will become more simple. So that means that this rule is not noise sensitive. For small amount of noise, the dynamical behavior will change for this rule. And there are, out of these 256 rules, we have identified that few rules can able to resist the noise. So from that we can able to understand what is the capacity of each and every rule according to some robustness. And I also want to mention another behavior. I'm taking another rule, and this behavior is important in terms of physics. Okay, so I'm taking rule. I'm just taking rule 50. Okay, rule 50. Rule 50. This is the behavior of rule 50. This is a kind of checkboard pattern. It will come up with checkboard pattern. This is rule 50, and now I'm adding noise to this rule. Okay, so if I put noise to this rule, let me add 70% updation probability. It will show checkerboard pattern, but the checkerboard pattern is disturbed due to this noise. Okay, and but it running, it is not converges. Converge means coming to a fixed point. After this convergence point, if we update the things again and again, the same thing will come. So now it is not converges, but the checkerboard pattern is disturbed. Now again, let me decrease the noise rate, and it will become, let me become 30%. And now if we update it for few time step, let me see suddenly what happened. It fighting with this noise, and finally after few time step, hopefully it will converge. Converge means all zero configuration will come. So after that, if we update it again and again, the same thing will come up again and again. So this change of behavior for this perturbation ratio, this thing you will call in terms of statistical physics, we'll call this phase transition. And this behavior is very exciting behavior in terms of statistical physics. So we can see that with if we apply this noise, we can see this phase transition kind of behavior. Okay, so interesting physical property also come out from these rules if we apply noise. So let me now talk about little bit of technology out of it, because till now whatever I'm talking purely science. Now let me introduce the possibilities that from this simple model, after applying this noise, is it possible to do any real technological things? So let me check. So I have done five five technological possibilities of this asynchronous system. One is pattern classification. One is there is a problem in distributed system, and also in blockchain, this consciousness problem, this density classification problem. This is a consciousness problem. Solving of this problem, modeling perspectives of this modeling of electoral dynamics in parliamentary dynamical system, crypto system, and random number generation. But due to lack of time, I cannot show all this technological application. I will choose two of them from this list. One is pattern classification, one is random number generation. Let me show them. So after applying this noise, few rules are converges. Converges means if we start from initial configuration, it will come to a configuration, and from there we cannot able to go anywhere. It will be stopped there. So there are two physical system properties in this world. One is convergence, one is reversibility. So if you observe anything in our nature, in our world, so there are two possibilities. One is convergence, one is reversibility. Convergence means it will come to a fixed point, and reversibility means it will never will come to any fixed point. It will moving on and moving on. This is reversibility. So if you observe any system in our reality, live, physical system, natural system, there are broadly two kind of behavior. So first kind of behavior is convergence. So I'm just running these rules. Suppose this is the initial configuration. So after this three step, it will come to a state which is a fixed point. It will moving on in this fixed point. So this is the example of one rule with four states only. So these are the dynamics of the basing of attractions. It will come to a convergent states. And I'm not talking about theory. So there are a few theorems and lemmas, all these things are there. We identify that out of these 256 rules, which rules are converges and which rules are not. So we have come up with these 32 rules, which are this first of all these 50 rules which converges to fixed point. But for designing a pattern classification, we need multiple fixed point. So after again applying some theory, we can able to characterize that these 32 rules after out of these 256 rules are converges to a fixed point. Okay, so now there are some convergence time, because if we try to design pattern classifier, then the rule should converge first. Otherwise, the pattern classifier will take a lot of time. So that is indeed not very much useful. So we also estimate the convergence time. So all these things are published. I have mentioned previous slides also. So finally, we identified that with these dynamics, we can able to design a pattern classifier, and it works very good with some 95% efficiency. It solves for one data set. There are we are working with multiple data sets, and it really competitive with the other complex algorithm. But here we have not applied any algorithm. We just use the natural dynamics of the system. What happened is that in case of pattern classifier, people are coming up with new algorithms, and the algorithms are pretty much critical. There are a lot of loops and all these things. If you read the pseudocode of these algorithms, it is very complex. But here we have not done nothing. We just run this simple program, and the evolution of the simple program is actually the algorithm, and it come up with a beautiful pattern classification algorithm. This is the first application. So with this simple program, you can even able to do pattern classification. And the important point is that here I am not doing anything. I'm just checking the capability of this simple program. I'm not coming up with any algorithms. I'm just observing the capability of this simple program. So this is the first application, and the second application is reversibility. So reversibility means there are circles. So if we start from a configuration, I'll moving on and moving on and moving on and moving on. Not like our life. Our life, there is a dead position, and that is the fixed point that converges. But reversibility is, the particles of this world are moving on and moving on. There are that kind of things you can imagine. So I just observed that which rule are reversible. So there are two kind of these cycles. One cycles we have characterized at fully exposed, and one cycle is partially exposed. So there are two kind of cycles, and let me show that some real pictures. So this is a cycle of one rule, and you can see that all the configurations are coming up with almost equal probability. If we run it again and again and again, suppose for a 8 cell there are 2 to the power 8, that means some number of configurations, and if we running it again and again, all the configurations coming up with equal probability. That means these fully expressed rules are good random number generator, and few rules are there are some hidden configurations. If we run it again and again, these configurations are coming up rarely. So this partially exposed system, again I'm doing nothing, I'm just observing the dynamics of this simple program with some noise. And so these hidden configurations that can be useful for generating crypto system. And this fully exposed system where each and every configuration is coming up with equal probability, so this system is useful for designing a good random number generator. Okay, so again there is a problem, because here we are using some asynchronous system, and for selecting these cells randomly, we are using in our programming a random number generator, right? Because if we want to select a particular cell for update with some probability, we need some random number generator. So therefore it actually, I'm generating random number from a random number generator. So what is the reality is, I'm actually seeing the randomness enhancing capability of this rule, and I'm coming up with that if we take a bad random number generator like rand, so rand passes almost two tests. There are some testing parameters. If you pass large number of tests, then the random number generator is good. If it pass less number of tests, then the random number generator is bad. All these things are there. So rand passes two tests, but if we apply rand as a random number generator in our Cellular Automata system, and if we evolve it, then it passes almost 10 tests out of the 13. Okay, so therefore it enhances the randomness capability of a bad random number generator. So this is another beautiful application, that I am with a bad random number generator and I'm just using this simple program. Okay, and I'm enhancing the capability of a bad random number generator. So this is up to so now delay sensitive cellular automata. I think I am with 20 minutes. So let me try to pick up with this within 5 minutes. So now I'm introducing another variant of noise. Previously it was asynchronism. Each and every cell is updated with different probability. Now I'm saying that okay, fine, you're talking about a mathematical model which is natural, but not purely natural, because each and every cell can able to know about their neighbors information without any delay. But in real life there are delays, there are information loss. Okay, so your model, you claiming that it's natural, it's close to nature, but not exactly close to nature, because you are excluding few factors that information will not be lost, there will be no delay. So in this noise I'm adding delay and information loss. And uh, with this uh, with this perturbation, I've just checked the rules, and there are 4 categories broadly. In one category, observe these 51 rules. This rule remain unchanged if we add delay and information loss. That means this rule is able to resist noise. That's the important key factor. Few rules can able to resist the noise. First I'm giving an example of this Chinese flash system. Okay, so for small noise, there is a in this rule for big noises also there will be no problem, and few rules changing their dynamics, but the number of 1 and number of 0, these things are conserved if we add noise. And there are few rules which are shows uh, different value, different behavior if we add noise. And here also for this different behavior, we identified this beautiful phase transition dynamics. The phases changes. There is a active phase for some noise, and there is a passive phase for some noise. And this behavior is really important in terms of statistical physics. So these are the graphs. This is the publication related with this after applying this noise. Okay, so finally few words. So we have seen that this model is can seen from 3 perspectives. One perspective is this is a discrete dynamical system. What I mean by discrete dynamical system? The properties of physical system in terms of physics. I'm talking about phase transition and all. So this dynamics can be observed, and reversibility. This is also a physical discrete dynamical system dynamics. So this dynamics, which is purely an interest of physicists and mathematicians, these dynamics are captured from this model. The second important point is that we can able to create some real technology. We can able to create also circuits and gates from this model. I have not shown that. So we can able to create a model of computation that can able to compute something, and in fact able to build technologies like crypto system, pattern classifier, like random number generator. The third point is that I'm saying that this model is uh, uh, doing computation following a natural phenomenon. Okay, so actually this model and its applications are actually opening a dialogue with computation and natural phenomenon. Okay, so that is very important point. So I'm claiming that this model of computation is behaving as a natural phenomenon, and from there the important key question which I can't able to answer. In fact, many of this generation people can't able to answer the question asked by Galileo, Leibniz. These peoples are asking that how computation Sorry, sorry, connection. So where I am last, so I'm concluding it, or so or not. Where I am.
Sir, I thought I had issues with my network. I couldn't. I think I got disconnected for last minute or so.
Okay. Uh, so uh,
So your screen is not shared, sir. I think it got discontinued. Rajesh, sir.
yeah, I'm discontinued, I think. So I'm with this slide, I think.
Yes, yes,
Is
Yes,
it
sir.
right?
Yes, sir. You were here.
yes, sir.
Okay. So so it is the concluding slides. So unfortunately, mm, so the last thing, last few words are the model is very simple. If there is any undergraduate student is there, try to just code this model. It will take 10 to 15 minutes if you know only array in any programming language. Then evolve the system, observe the beauty of the system, and there is a $30,000 prize for solving uh, this simple thing. So you can try it and have fun, all these things. And so that here I'm actually stopping. So if you want to ask any question, so then you can ask me.
Hello. Hello. Anyone have any questions regarding this or any doubt?
Sir, I
Ma'am.
have a question.
Yes,
Yes,
yes.
sure.
Please raise your question.
Sir, I was actually wondering what kind of simulation tools can be useful in this area, like which.
There are lots of tools. One of my collaborator Najim Fets, there is a tool called Fatlex, FATLEX, Najim Fets. So there is a simulator, but if you want to program it, it will take 10 to 15 minutes. So you can build your own simulator because this is nothing but updating a array with by following a simple rule. There is nothing else.
So,
Any more questions from the audience?
sir, I think
Yes, sir.
many of the.
Hello,
Yes, please,
excuse me.
somebody.
Yes, Pandan, you can ask.
Yes, sir. So my question was initially the array size will be what, sir?
So you can take any array size. If you
Sir,
do
it
math,
is.
array size maybe 10, 15, 2000, 200, anything you can take.
So
The
here,
behavior,
sir, the size is increasing or it is remaining same.
so you will just update the array each and every time. So two array will be sufficient of same size. So uh, we just replacing the array and plotting it. So you can take any size. And for doing mathematics, you have to consider array size infinite. If you try to mathematically theorize something,
Madam, 10
then we have to take infinite array size. Uh, that's a problem uh, for theorization.
Sir, in rule 30, we're taking one as the initial in the array. We're taking one. So
The middle one is one.
yes, sir. Yes. So it is only mandatory to take one, and or you can change that one.
For that problem, middle one should be one. But you can start with any initial configuration and see the
For
evolution
other
of this.
patterns.
Yeah, all the patterns. And there are chaotic patterns are there. So you can try to characterize the pattern, try to identify the properties of chaos in this pattern, all these things you can do. Thank you.
Thank you, sir.
Okay. So, ma'am, can I conclude? Madhuri, ma'am. Hello.
Yes, sir,
Oh,
sir.
okay.
But if, sir, sorry, sir, I'm just requesting if it's possible to get your PPT because later students follow up,
Yeah,
and
I will
we
send.
also have, so we
I'll
also have
send.
a YouTube recording and we have a YouTube channel. So students do go through it and actually connect us, and
I'll
they
send you
see.
right back.
So,
And sir, one
Rajesh,
more
sir,
thing,
please go
sir.
ahead.
Yeah.
So
Oh,
can I
okay.
can we get the programs of the Python program?
Okay, okay, I'll send you the Python program. Okay.
Okay, sir. Thank you.
Okay. Acha. Okay, I think sir, I think this session was very interesting and more practical oriented. And sir is also attached with us, so don't, if you are getting any problem, any questions, so you also can ask to me, to the sir. And also now, so now we are going to conclude this session. So now I want to thanks all the participants who are present in this particular webinar for today's sessions. So I express my gratitude and warm welcome to Dr. Souvik Roy for sharing his knowledge and spending his precious time with us. So I also want to thank our CSE HOD for encouraging me to organize such a webinar. And also I want to thank uh, Madhuri Madam for sharing his knowledge and helping me to organize this particular as a webinar. So once again, I also want to thank all the faculty members of our department, participants, and our precious guest, Dr. Souvik Roy. Thank you. Thank you to all of you.
Thank you very much. Have a nice
Sir,
weekend.
I think I also need to thank Rajesh sir for getting us such a wonderful speaker. And sir, this topic is so challenging, and you have so beautifully explained, made us think. And sir, I think this weekend some of it I will also explore. So thank you so much, sir.
Okay,
Thank you. Thank you. Thank you.
Thank you, Rajesh sir. Thank you.
Thank you. Thank you to all of you. Thank you, sir. Thank you, Souvik, sir.
thank you. Bye. Have a nice weekend.
Okay.
Thank
Thank
you.
you.
Stay
Thank
living.